In this lesson, we're going to look at the various properties of limits, and you can see the properties are listed right here in this table. So the limit of a constant as x approaches a is just equal to that constant. The limit of x as x approaches a, well, you just directly substitute and that equals to a. Notice here that the limit as x approaches a of two functions that are added or subtracted from each other, you can break this up into, say, the limit of f of x as x approaches a and the limit of g of x as x approaches a. You can separate them accordingly. If you have a constant in front of the function, you can factor that constant out and just evaluate the limit of that function and then apply the constant. If you have two functions that are multiplied by each other, you can individually find the limits and then multiply those two limits together. If you have two functions that are being divided, you can find the limit of the numerator function and then the limit of the denominator function, provided that the denominator function does not equal to 0. Finally, if you have the limit of a function raised to the power of n, you can find the limit of the function and then raise that entire limit to the power of n. We're going to start by showing that the following is true using direct substitution in the properties above. Well, as we can see here, we have a function that's made up of multiple terms, right? So this is like a quadratic function plus a linear function minus a constant function, right? So that is this property right here. We have a series of functions added and subtracted together. So we're going to split this up and find the limit of each of these individual terms. Okay, so let's prove this, and let's start by looking at the left side. Well, the left side is equal to the limit as x approaches 2 of 3x squared plus 4x minus 1. I can use direct substitution there. 2 squared plus 4 times 2 minus 1, and I get 19. Okay, so that's evaluating the limit of all these terms together. Now, what I can do is I can separate these terms and treat them as individual functions: a quadratic function, a linear function, and a constant function. So the limit as x approaches 2 of 3x squared plus the limit as x approaches 2 of 4x minus the limit as x approaches 2 of the constant 1. Using direct substitution in the first one, this is just simply 3 times 2 squared plus, again, direct substitution, 4 times 2. And remember, the limit of a constant is just equal to that constant. And we end up with, again, 19. So we've shown here that if you have several terms added or subtracted together within a limit, you can break it up into several different limits. Using direct substitution to evaluate the following limits, well, again, if I have, as we can see here, I've got a quadratic in the numerator and a cubic in the denominator, I can use this property right here and just find the limit of the top divided by the limit of the bottom. And so all I have to do there is just do some direct substitution. So in this case, it's negative 1 squared minus 5, negative 1 plus 2, all over 2 negative 1 cubed plus 3 times negative 1 plus 1, and that comes to negative 2. Over here, again, I can use direct substitution here. I don't have to worry about indeterminate form because I'm not going to have 0 over 0. And so I can just say that this is this right here is square root of 5 squared over 5 minus 1. All right, so that gets me 25 over 4, all square rooted. And that means now I can apply the square root to the numerator and the square root to the denominator, and I get 5 over 2. If using substitution would result in the indeterminate form, we can use other techniques to evaluate the limit. So if we end up with this indeterminate form, so for example, if I look at this, right, if I substituted a 3 directly into this function here, I would end up with 0 over 0. So we can try algebraic techniques such as factoring to see if this would help our situation and get us out of indeterminate form. So what I'm going to do is I'm going to write the limit as x approaches 3. And in the numerator here, I'm going to factor this trinomial, and I get x minus 3x plus 1 all over x minus 3. This is perfect because this cancels this binomial factor, goes to 1. And so now I have the limit as x approaches 3 of x plus 1. And then directly substituting in, I get 4. We can also rationalize the numerator or denominator to determine a limit. And when we say rationalizing the numerator or denominator, this may involve using a conjugate binomial. So if I look right here, this is my binomial. This will be my a, that's my b, so a minus b. So the conjugate binomial, so I'm going to take this limit again, square root x plus 1 minus 1 all over x, and I'm going to multiply by its conjugate binomial, which is the square root of x plus 1 all over the square root of x plus 1 plus 1. And you will recall that in the numerator that produces a difference of squares, a minus b times a plus b. So that gives me the limit as x approaches 0 of, and then brackets, square root of x plus 1 all squared minus 1 all squared, in the denominator x bracket square root of x plus 1 plus 1. Okay, let's continue on. This term right here simply becomes x plus 1. This term right here simply becomes minus 1 all over x bracket square root of x plus 1 plus 1. You can see that the numerator simplifies to x all over x square root x plus 1 plus 1. These x's will cancel. Simplifies to 1. Sorry, I forgot the 0 there. Okay. And I end up with the limit as x approaches 0 of 1 over the, again, square root of x plus 1 plus 1. And so now I can directly substitute, and I get 1 over square root of 0 plus 1 plus 1, and I get 1 over 2. For some functions, you may want to graph it if you are unable to use any of the above methods or as a final resort. In this case, you need to evaluate the limit approaching from the left and the limit approaching from the right. So we're going to evaluate this limit using a graph of the function. So let's check to see if this limit exists. So I'm going to use my one-sided limits. So I'm going to say right here, so I'll write use one-sided limits. Okay, and I will say the limit as x approaches 2 from the negative side of f at x being this function right here, or this right here. Okay, and let's look on my graph. So approaching from the negative side, right here. Okay, so as x approaches 2 from the negative side, y approaches 1, or rather negative 1. Limit as x approaches 2 from the positive side. So, okay, so I go from this side right there. This is as x approaches 2 from the positive side. Y is going to approach positive 1 in this case. So, since the limit as x approaches 2 from the negative of f at x does not equal the limit as x approaches 2 from the positive side of f at x, the limit as x approaches 2 of f at x does not exist. We can also use u substitution to evaluate limits if we are in an indeterminate form. So some limits will require you to change the variable in the question to work around indeterminate form. This is sometimes referred to as u substitution since the variable is changed to u. Note well that the value that u approaches may also change as well. So we're going to have to change this expression right here using u, and we'll also have to change the limit value as well. So what I'm going to do here is I'm going to look at this x to the power of 1 over 3, and I'm going to use my u substitution there. So what I will say, here, I'll just make sure that I've got enough room here. Okay, I'm going to say let u represent x to the power of 1 over 3. So what this means now is u is equal to x to the power of 1 over 3. And if I cube both sides, I can therefore now say, therefore, u cubed is equal to x. All right, so I now have a value for x to the power of 1 over 3. X to the power of 1 over 3 is just u, and x is u cubed. Okay, so I'm going to write over here, and I'm going to be careful. I'm not going to write with the bottom portion of this limit yet because I want to show you what's going to happen there. But instead of x to the power of 1 over 3, x to the power of 1 over 3 is just u. So u minus 3 all over. And in the denominator here, I have x minus 27. Well, we just showed that x is equal to u cubed. So u cubed minus 27. But as I stated previously, note the value that u approaches may change as well. So not only did I modify the variable, I also have to modify the value in the limit. Okay, so let's think about this for a second. The limit is as x approaches 27. So as x approaches 27, so as this value approaches 27, u cubed, right? Since x and u cubed are the same, u cubed approaches 27. And that would mean if I cube root both sides, therefore u is going to approach 3. So I now have my new value in the limit, which is u is approaching 3. Now you may say, well, that's still in indeterminate form. That's true. However, we can recall that we have a difference of cubes in the denominator, and that might allow us to factor something out. So the limit as u approaches 3 of u minus 3, and then in the denominator I have u cubed minus 27. Well, that factors into u minus 3, and then u squared plus 3u plus 9 in the denominator. And as we can see now, this will cancel. The limit as u approaches 3, and then I have 1 all over u squared plus 3u plus 9. I can perform a direct substitution in, and I get 1 over 27. So just to review, I look at this right here, and I take this term right here, x to the power of 1 over 3, and I say let u represent x to the power of 1 over 3. If u is equal to x to the 1 over 3, then that means u cubed would just be x. And if x approaches 27, if this value approaches 27, then u cubed also approaches 27, which would mean that u has to approach 3, right? Because 3 cubed would give you 27. So the u value there is 3. So that causes me to change this limit value right here. Instead of x going to 27, I'm saying u is going to 3. I do some u substitution here for x to the power of 1 over 3. That's just u, right? And x is u cubed, so I do that. I use my difference of cubes, and I evaluate the limit. Okay. Now we can make this a little bit more complex. And what I will say here is I'm going to take this value right here, so this x plus 8 all to the power of 1 over 3. I'm going to say let u represent x plus 8 all raised to the power of 1 over 3. Okay, so therefore u is equal to x plus 8 all to the power of 1 over 3. I'm going to cube both sides again. And so u cubed would just simply be equal to x plus 8. And if I want to find what just x is, I can bring this 8 over to the other side, and u cubed minus 8 is equal to x. Okay, so I have what u is equal to. U is equal to x plus 8 to the power of 1 over 3. I have what x is equal to. X is equal to u cubed minus 8. Great. Now I need to think about this portion of the limit. All right, well, let's think about this. As x approaches 0, well, as x approaches 0, if this value is going towards 0, that means u cubed minus 8 is approaching 0. So what's the value of u right there? So we think about that, that means u cubed has to approach 8, and therefore u has to approach 2. So now that I've done all this work, I can rewrite this entire limit in terms of u. So let's rewrite this now in terms of u. The limit, and not as x approaches 0, but as u approaches 2. And in the numerator right here, I said that u represents x plus 8 to the 1/3, so that's going to be u minus 2. And I know that x is equal to u cubed minus 8. So the limit as u approaches 2 of u minus 2, and then in the denominator, again, that's the difference of cubes, so u minus 2, and then I have u squared plus 2u plus 4. I can see that these cancel. I have the limit as u approaches 2 of 1 all over u squared plus 2u plus 4. I perform my direct substitution, and I get 1 over 12. Thanks for watching.